So we're continuing on. If we state the domains and range of f at x, so if we look at f at x, the domain and range for f at x, well, the domain for f, it's just a parabola, so the domain is x such that x is an element, such that x is an element of reals. And the range for f is a parabola that has its vertex at 0, -3, so its range is y such that y is greater than or equal to -3, and y is an element of reals. And if we look at function g, what's its domain? Well, the domain of function g, that's a square root function, so x such that x must be greater than or equal to 1. X is an element of reals. And the range of that square root function is y such that y is greater than or equal to 0. And y is an element of reals. It says in order to determine the domain and range of FOG and GOF, Aaron decided to graph it in his calculator for FOG and GOF, and he used his graphing calculator to sketch the graphs. He obtained the following, and so he concluded that the domain of FOG was real numbers, because when he graphed the actual expressions for it, he got a straight line, so clearly the domain and the range were real numbers. For GOF, he got the domain and range to be x is less than or equal to -2, greater than or equal to 2, and y is greater than or equal to 1. Now that's partly because his calculator maybe wasn't set right? But that can happen, right? There are errors in his thinking. So if we look and we find expressions for each of these, when you do f at g at x, so if we look at f at g at x, we have f and g at x is, I guess gotta go back and remember what g at x was. So we've got f with square root x minus 1 that's inside of it. And now when we do the function, that means that we will take and we will take the square root of x minus 1 and we'll square it, and then we will subtract 3, which ends up being x minus 1 minus 3, which is really just x minus 4, a straight line. That's handy. If we do g at f at x, we know that f at x is equal to x squared minus 3. So if we put that inside of g, we end up with the square root of x squared minus 3 minus 1, which then becomes the square root of x squared minus 4. And when we look at these things, it asks us we found expressions for those. And when we look at these things, clearly you can see that. So what Aaron forgot to consider is that when his input was the square root of x minus 1, we have to remember that that function has a domain of x is greater than or equal to 1. So even though in the end you get a nice little function like this where you think that x is an element of reals, and that's why the calculator graphed this, you still have to remember that there is a restriction on the domain. Kind of like when you have rational functions and you cancel out, when you have a rational function and you cancel out g at x, whoopsie, we still have to remember that if we have rational functions and we have x plus 3 over x plus 1 all over x plus 1, we know that even though we canceled out x plus 1 and x plus 1, we still have a non-permissible value of x cannot be equal to -1. And that's what we have to be aware of here too. Even though that function is x minus 4, we still have a domain restriction of x must still be greater than or equal to 1. And because of that, it also obviously affects the range, right? So when we graph f at g at x, we don't get a solid line, we get a line that actually starts from 1 and minus 5, 1 and minus 3. 1 and minus 3, and then carries on and upward. And the domain of FOG at x is x such that x is greater than or equal to 1. X is an element of reals. And the range is y such that y is greater than or equal to minus 3, and y is an element of reals. Now you give GOF a try and see what you think that one is. So Aaron was fairly close with his graph of g of f at x. And when you do graph that one, you can see, hopefully by the equation that he had, you cannot have a number that's smaller than 2. 2 makes it 0. So you have to be aware that x is greater than or equal to 2, or it's less than or equal to minus 2, so that you aren't taking the square root of a negative in that g of f at x function. So that's the domain of f at x. It's more restricted than it was when you look at the inner function. The inner function used to have a restriction of all real numbers, f at x, the inner function there, but now it's much more restricted because of the square root function. And we cannot make that greater than, we cannot make that less than 0, because obviously the radical is a positive radical and we can't make it negative. What's the lesson in domain and range? We have to keep track of what we're subbing into the function, what's my input, and be aware that the restrictions on my input, no matter what happens algebraically, we have to maintain that awareness of the inputs. And that's why it says on this that when you calculate an expression, there may be restrictions on domain and range. In most cases, domain and range of composite functions are different than what they were originally in the original functions. But what's really important is you can never have more domain in the composite function than you had in the domain of the inner function before. Now, when you look at this, the way they worded it, G is the inner function. It's the one you're subbing into F. So you can't have more domain on the composite function than you had on the one you were inputting. So that's important. And the range of the composite function f of g, or f of g at x, you can't have more range on the composite function than you had on the outer function, right? So this is the outer, and that is the outer there. And how you worded it is important. All right? I want you to give the assignment a go, and if we have questions, we will deal with them tomorrow. Good job, Math 30.